Welcome to TxGIS Day 2020, a quick A to Z guide on capturing the real world using PhoDAR. I will start by introducing myself. My name is Ishka Voiculescu and I'm a jack of all trades within City of Austin's Public Works Department. I'm also known as Ishka or Dish, and you can find me on Twitter or LinkedIn. For the background, I'm a mechanical engineer that jumped ship to civil engineering. For experience, I have 18 years of combined experience with Autodesk, Bentley, S3 and other products, and 15 of those are in civil, surveying, GIS, and UAS, or drones. As a daily job, I'm working on training, standards, and implementation of things within public works. I'm also a US Part 107 certified pilot for Public Works Department. What we will cover today: first, context. We're going to talk about PhoDAR and what is PhoDAR. Then is the tools of the trade. That means the drones. They are the tools that enable the generation of PhoDAR. We're gonna talk about capturing the data, planning and execution, and we're gonna talk about processing the data, platforms and deliverables. So for the context, what is PhoDAR? And when it comes about PhoDAR, it's a word that actually joins two words. One is photography, and the other one is LiDAR to express a workflow. So in the image on the right side, we have an image like pretty much a camera image that is converted at the end in a 3D point cloud. And PhoDAR achieves this one via a process that is called aerotriangulation. So this technology creates a 3D point cloud and 3D point cloud derived products by processing high resolution aerial imagery. We'll make a little comparison between LiDAR and PhoDAR. So when it comes about the LiDAR, the sensor for the LiDAR, it's a LiDAR module that sends laser beams to the ground and measures the return of those laser beams and records that return in the point cloud. The application is the data for, the data as just mentioned, it's a point cloud that comes out of the LiDAR. The application for this type of technology is typically used for open areas or relatively dense vegetation. If you have very dense vegetation, then LiDAR is not used because the laser beams, they cannot reach the ground, so you cannot get data back from the ground. Yeah, that's why at most relatively dense vegetation. The cost for the LiDAR is relatively mid to high cost, high range. For example, for a LiDAR module, the camera, it's $60,000 to almost $500,000 for the module. And the drone frame typically ranges at $20,000 or so. And when it comes about PhoDAR, the sensor on the PhoDAR is actually a camera module. It's like a regular camera. And the camera captures overlapping imagery, as you see from the image, the overlapping imagery. And the sensor at this moment is important because the color quality of the image defines the quality of the output. More pixels don't necessarily mean better output. The data that we get from PhoDAR is imagery, overlapping imagery, that are going to be converted to point clouds in post-processing. So whether LiDAR or PhoDAR, the output is the same, it's a point cloud. And the application for this type of technology, it's open areas and relatively open vegetation areas. If the camera can see it, it can be mapped. And if you don't mow your grass, of course, you're not going to get good results. The cost for this technology is relatively affordable, with ranging from $1,000 to almost $50,000 for the setup. We're going to switch to tools of the trade, the drones. And what options do we have? We have consumer drones, with DJI Phantoms, Inspires, Mavics, or 3DRs. They can be also other providers like Alltel and so. We have industrial drones, DJI Matrice or Phantom 4 RTK. The difference in between them is that the industrial drones, they have an RTK module added to them or more technology added to them that makes the mapping of data more accurate. And then we have platform solutions, like, and some of them might be Precision Hawk or Drone Deploy or others, yeah. We're gonna switch to capturing the data, and we're gonna provide here the workflow to capture the data. And the question is, what do I need to do? The first things is check the requirements for the flight, and here we consider the area to be flown, conditions, and constraints. And the questions you might pose, it's how much coverage area needs to be mapped, because based on the area to be mapped, it might require more time. Depending on the altitude to be mapped, you might require like more flights or less flights. Based on the resolution of the data that you want to get, an altitude might be more suitable than the other one. Yeah, getting closer to the ground doesn't necessarily improve the results because there are less reference points to be mapped. And when we talk about photogrammetry, we have a concept of GSD, or the ground sample distance, and the ground sample distance defines the resolution of the data. And for example, for a Phantom 4 RTK at 150 feet, you have a 0.49 inch per pixel resolution, while from the same height for Inspire 2 with an X5S camera, we have actually a better resolution at 0.39. Calculators for the GSD can be found online with a simple Google search. You also have to consider the conditions, like consider the weather conditions, consider the wind speed, vegetation, and structures. Yeah, for example, weather conditions, you might think about like if you're flying on a sunny day, you're gonna get a better result than flying on a very overclouded day. You might think about like wind speed, very high wind speed, you're gonna have a lot of vibration and movement of the camera. Another thing to consider, like if you have lots of vegetation, you'll be harder to map that area, and you might have to consider about the structures. Think about, for example, like electrical power poles that might affect your mapping, might affect your height at which you can fly. And among the constraints, I would think about airspace approvals and other approvals, because if you have to fly in a restricted area, you need approvals for that area. The next step in here is to plan the flight. What do you try to get out of the flight? You want to get NADIR, you want to get like oblique shots, or you want to get a mix of NADIR and obliques. Now, planning the flight can be done with automated tools, and these tools, they can be found online. And I have some example as Pix4D or Drone Deploy. They can in these tools you can plan your flight, and at the same time when you're in the field, execute it. So these tools, they allow for the definition of the overlap between the front and side shots, camera exposure, and so much more. The next step would be to set up the ground control points using targets for best accuracy. So the data, what you're going to get outside, what you can get is a point cloud, and this point cloud will be more accurate if you have some tie-in points. That means the ground control points. And the data for the ground control points is collected prior to the flight and then marked on the ground to be visible from the imagery. And the last step is to execute the flight and check the collected data. And as you see from the image, I have an RTK station there, and the UAV is up in the sky, and the flight is executed. And once it's finalized, the drone, using the automated tools, returns back to home. And we can see it coming back home once it finalized the flight. The last thing we're going to focus on is processing the data, and the workflow for this one is pretty much processing the data back in the office, because the data, you can process some of it in the field, but the data is processed back in the office. So how do I get from field to finish? How I get the data to be processed, and at the end to get my output? The first thing is going to be to choose the processing platform, and here we have an option of SGGeoMap, Pix4D, EGSAM Metashape, Bentley Context Capture, and Web ODM. So in here, the first one is the Geontmap. It's relatively new to the field and uses a licensed Pix4D engine to process the data. It comes up, it's sometimes very integrated with all the Esri products, so it's one of the platforms you can consider. The next one is a Pix4D, and Pix4D is one of the originals, as I call them, typically the platform used by people that want a user-friendly processing, and they have a very good support via forums. The next one is EGSAM Metashape, one of the best platforms for processing the data, with a lot of control and maybe too much control on how to process the data, and we have a very good support via forums. Another platform is Bentley Context Capture, one of the originals, formerly known as Acute3D, rebranded once purchased by Bentley. Best overall platform to process the data that allows integration of multiple types of point cloud products to be used in processing the final photogrammetric product. Aerial PhoDAR can be integrated with static or mobile laser scanner data to generate the final product. And the last one here is a Web ODM. It's an open source platform that can be installed and deployed in the organization to process the data. The next step is to define the processing type, what you try to achieve out of the data. Do you want to achieve like an orthomosaic? Do you want to get a point cloud as in the 3D model or so? Or you want to make a mix of it? Some of the software allows for a specific 2D processing, sometimes it allows for 3D, and the parameters for processing the data were customized based on the choice of the user. So if you see right in here, we have this one. It's a top shots. So pay attention. This is a top shot, only. It's a NADIR shot. So if you see here the 3D model, it's NADIR only. While in here, this one is the same model, but includes oblique shots. So instead of having nadir shots, this one uses the oblique shots, and you're gonna get a better result out of it. And the last one, this is use a combination of both top and oblique shots to get an even better result. The first step to process the data, it will be to import the imagery. When you import the imagery, will be imported and the settings for the imagery adjusted. Sometimes the camera setup will need to be calibrated from the stock camera that comes with the software. The next step is to align the imagery and generate a sparse cloud. The imagery will go through a process of aligning against each other based on the georeference data. Software will find common points or tie points in each photo, and that is how it will generate the sparse cloud of the tie points. This is typically the fastest step of the process compared with the other steps in the workflow. Once the sparse cloud is processed, this one will have to be adjusted with ground control points. So if you have ground control data, at this moment you're going to align the sparse cloud with those ground control points. So if you have the ground control, these points will need to be identified in the sparse point cloud, and the sparse point cloud will need to be readjusted based on this point data. And if you see from the image, I find the point. It's pretty much the mark point on the ground, and I can find it also in the sparse point cloud, and then the data will have to be readjusted. The next step is the most intensive step, is to generate the dense point cloud. The software will use the sparse point cloud and generate the densified point cloud of all the data. This is a step that requires the most resources and most intensive on the machine it runs on. It can take from hours to days to complete based on the size of the project and the settings on the quality of the processing. Sometimes the software provider might offer to process this data in the cloud. Keep in mind that this is the product that all other deliverables require as a source for generation. Depending on the platform, the dense point cloud can be generated in an industry standard format as LAS or other custom formats. The next thing, you can export a mesh, pretty much is a 3D object of that's generated from the point cloud. So using the dense point cloud, we generate a mesh product in a format that can be used in multiple platforms for visualization. OBJ, SLPK, that's the scene layer package, and sometimes even KML. At the end, you can actually generate an DEM, DSM, or orthomosaic, a NADIR, and they will be generated using the mesh as a source, and the DSM and the DEM will be generated using the dense point cloud. And the final question is, does the platform matter? What do I recommend, or what is recommended? Remember that our main deliverable product is a point cloud file. All the other deliverables are as good as your dense point cloud is. We tested the same dataset in multiple platforms to find which we could rely on for a good product. And you can look at the video that it's in the presentation to see the difference. So here we have the first platform is a Pix4D, and this one it's a shot made from oblique shots. So pretty much, it's a product generated from Pix4D. Then you're gonna transition to AGSoft Meta Shape, and you're gonna see the difference. So the same product, the same data used, and there's a whole lot of difference in between the Pix4D and Meta Shape. And the last one, the same data used in context capture. So in a little bit, we're going to transition to context capture and look at the data. So this is the same data in context capture, and the quality of the processing gets even better. So if it comes about the processing platform, as I said before, your output data is as good as the point cloud that's processed. Yeah. So because of that one, I would say, my recommendation for the platform to process your photogrammetry model, it would be context capture from Bentley. And we end up here with the questions and answers slide. Any questions, you can find me using the information that's found on this slide. Thank you for attending the TxGIS Day 2020 and for allowing me to present this to you.